Okay, so I think at the end of class last time, we were right in the middle of the Fermat numbers. Is that right? Do you remember where we stopped? Where we stopped? Round and around and around she goes. Where she stops, nobody knows. We were doing a perfect number. Let's start here. Review this, where we were. Remember we said the perfect number, with a perfect number, the sum of its divisors is twice the number. So in this particular example, the divisors of 6 are 1, 2, 3, and 6. And if you add 1 plus 2 plus 3 plus 6, you get 12, which is 2 times 6. And then we said, suppose you have a function sum of divisors that returns the sum of the divisors of number n, and it has one parameter. And then we said, how would you write perfect? Such that perfect 4 returns false, perfect 5 returns false, but perfect 6 returns true, etc. And then we said that what you would do is you would just write, it would be a one-liner. I don't remember, did we actually write that one-liner last time or not? Do you remember? You don't think so? Oh, you do think so. Okay, well, and then we said, then we started talking about the shape of sum of divisors. So now, and here was an interesting concept. So here we have, on this slide, define sum of divisors, and we have lambda n, because n is the number for which we're finding the sum of divisors. And then we said, at the bottom, there's only going to be, it's a one-liner. At the bottom, we're going to call sum from plus 1, 0. And we said that what we're going to do here is sum from plus is defined inside of sum of divisors. Now the reason that we want to do it this way is because if it was defined outside of sum of divisors, it would not have access to n. But this way, it's going to have access to n. All right? And you can do this. You can put the definition of one function inside of another function. And when it's in there, it has access to all the parameters that any other function, any other statement in scheme has access to. All right? So sum from plus is defined inside sum of divisors. So it has access to n. And then we said that these two parameters here in sum from plus, the first one is low, and the second one is add-end. And then we have this very important statement here, which is the specification of sum from plus. And what it does is the following. Sum from plus returns the sum of all the divisors of n that are greater than or equal to low plus the add-end. So we said that if that's what sum from plus returns, what does it return when we call it with low of 1 and an add-end of 0? So let's just state that with low of 1 and add-end of 0. Sum from plus returns the sum of all the divisors of n that are greater than or equal to 1 plus what?
0.
Plus 0. So do you see then that if we call it with those values for low and add-end, if it does what it says it's supposed to do, it will return, in fact, the sum of all the divisors of the number. Is everybody clear on that? On how that, what that means? All right. So here again is the specification for sum from plus, and I think we ended right with this figure. We're going to do an example for 12. So how do we know if 12 is perfect? Well, we write down all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the integers that are less than or equal to 12, all the positive integers that are less than or equal to 12. And what we would have to do is we would have to test each one of those and see if it divides 12. And if it does, then we need to accumulate it into the, what did we call it? Into the add-end. Okay, so here in this particular example, n is equal to 12. Are you with me? And the example that we gave was a low equal to 6, right? So now if n is 12 and low is 6, in this particular example, what will the addend be? The addend is going to contain, this is going to be the invariant. The addend is going to contain the sum of all the divisors of n that are less than low. Are you with me on that? The addend is going to contain the sum of all the divisors of n that are less than low. That's the invariant. That will always happen each time through the loop. Not through the, it's not a loop. Well, I mean, each time, at each recursive step, we maintain that invariant. All right? So the question is, and here's where we ended last time. The question is, how do we get one more step, how do we increase low by 1? Because see, what's going to happen is each time we call it, we're going to call it with a 1 bigger value of low. But if we call it recursively with 1 bigger value of low, then what do we have to do to the addend? And here's where we ended in class last time. What do we have to do with the addend? So can you tell me just in English, in words?
You have to figure out if low divides n or not.
You have to figure out if low divides n or not. And if, yes. And if it does, you have to add it to addend. And then each time we go up, low will just keep getting bigger and bigger and bigger. And each time it goes up, if low, if that value is, if it does divide it, we add it. If it doesn't divide it, we don't. But in either case, we go up, and the addend will contain all the, will still contain the sum of the divisors of all the integers that are less than, the divisors of n of all the integers that are less than low. So the example here is, eventually when we do this recursively, one of the calls will be sum from plus 6, 10. And this is the picture of what that will be. So now look, you guys, if you understand that, it's not that difficult to write the code. So here we go. Let's see if we can do it. What's the first? We have a blank slate here. So what are we defining?
Define sum from plus.
Yeah, we're going to define sum from plus. So the first thing is going to be define sum from plus. And how many parameters? 2. So lambda, low addend. Is everybody with me on this? On these two, right? Is everybody clear? See if you can anticipate this. Define sum from plus, sum of all the divisors of n which are greater than or equal to low plus addend. So sum from plus, low addend. So now what does every recursive, it's going to be recursive, right? And so what's the base case going to be? If, yeah, but if what? What? You're right, it'll be if, but if what? I mean, just...
Low equals n.
Yeah, if low equals n, then we're at the end. And what do we return in that case? Not necessarily plus low.
Well, because aren't we doing that? Isn't it comparing what this returns to 2 times n? So
You return low, right?
Oh, but this is just sum of divisors. The perfect, remember there will be a function, another function called perfect. And perfect will be a one-liner that calls sum of divisors, and the perfect will make that comparison.
yeah. Well, we wrote perfect and we had to compare sum divisors n to n times 2.
Yeah, so we don't need to do that inside sum of divisors. Sum of divisors just returns the sum of divisors. Was that your question?
Okay.
Are you with me on this? So yeah, the code. Oh, we did that. So yeah, the code inside perfect will do that. So all we have to do is return the sum of the divisors. So what will we return in the base case? Just the add-in. So if greater than low n, right? So what have we done here? We've gone one past, right? So, and you are right, it's add-in. So no divisors of n are greater than n. But now what? Huh?
For the false, you need another if, right?
Do we need another, oh, I guess we do need another if, because we have to return one thing. We we have to return one thing or another depending on if it divides.
But
You're-
we're not returning, are we passing it to something plus? One thing passing.
Well, oh, good question. Yeah, no, the answer is we are returning. What do functions always do?
Well, I meant, isn't the thing that changes one of the things we're passing to something plus when we call it again?
Wait, say that again? I think we need an if here because we have to check to see if it divides. We have to check to see that if it divides. But we are returning something, right? Because look, what does sum from plus? It returns, what is it? Here it says, what does it return? The sum of all the divisors which are greater than or equal to low plus add-in. So, we don't need an if on this line. It's sum from plus because we know that the first parameter is going to be one more. Yeah? Because that's the low. So we're going to call it recursively with low being low plus 1. And now's where we need the if. Yeah, I was mistaken. And here's where we need the if. So now what do we have to check? So now we have to check if what? If it. Now what do we have to check? Didn't we write a divides? I think we wrote divides, did we not? So what do we have to check if what divides, then we do what? So what do we have to check divides what? Yeah, we have to see if low divides n. Okay, so that's if divides low n. Now if that's true, what do we have to return?
Sum from plus low 1 and plus add n low.
No. We're calling sum from plus. I don't think we return another sum from plus.
Would be plus
Are you with me?
add-in then.
Yes, we have to add, it's our current add-end plus, not n, not n, would it be, wouldn't it be low?
Low, yeah.
Okay, so if it divides, then we return low plus the add-end. Otherwise, what do we return?
Add-in.
Just the add-end, we don't add it. Yeah, otherwise it's just the add-in. And that's it. Huh? Are we good? Now the thing is, I don't think I'll take the time to demo this, but you can have faith, brother. Brothers and sisters, have faith. This does actually work. Now, so here's the thing. Let's see. Okay, so here's our demo, and here is sum of divisors. And if we run it, let's do a little test. Now, actually, Ray had a good question last time. If we do perfect 4, what should that be? False, and it works. Perfect 5. And that works. And now what should we get for perfect 6? That works, right? Because that's true. And now the question is, what's the next perfect number? And trust me, perfect 7 is not 7 is not perfect. We could do 8 and 9 and 10 and 11. So now the question is, what is the first perfect number after 6? So here's what we need, you guys. We need this. We need something, we need to do this. We need to do first perfect after. And then if I put first perfect after 6 and press return, what that needs to do is what? Yeah, figure out the first rate. So now how can we do that? Do you see how can we write first perfect after? Let's do it. I don't want to do it here because, I didn't want to do it there because it's undefined. So let's, actually, this one I think I'm just going to try defining right here. Define first perfect after. No, I take it back. I am going to define it up here. I kind of hated to. Let's do it here. Define first perfect after. Okay, and now what always goes here? Lambda. And how many parameters does first perfect after have? 1. And now you guys, this should be pretty easy. What do? What should we test? What's the base case? Say it again? Yeah, check to see if perfect, yeah, we should check to see if n plus 1 is perfect. So how do we check that? So what's the test? If? Oh yes, if equals, well, no, not equals. Because it equals what? Because what function do we have to work with?
Would you be able to do equals and then perfect, n plus 1,
Aha.
and then hash, or true?
Oh, but that's redundant. Yeah, oh, yeah. Okay, look, you guys. Why, yeah. Yes, yeah, that's redundant. When you say perfect equals true, the equals true is redundant. Are you with me? Yeah, you were going to, I thought you were going to check it equals with an integer, but no, you're going to check it with true. But that's redundant. Because, why is that? That's because true is the identity for equals, right? Perfect, good. If perfect, what now? If what's perfect? Plus n1, okay. And so now there's that. And if that's true, if that is, then what do we return? Yeah, plus n1, okay. Otherwise, what do we return? First perfect after. Yeah, first perfect after what? Plus n1. Oh, this is really good. You guys are good. Okay, so let's run this. Now, Ray, here's the answer to your big question. First perfect. Does anybody want to guess how big this number is? Ha, you already know. First perfect after 6. It is 28. So now what's your next question? Anybody want to guess anyone want to guess the next one? First perfect after
496.
28. Yeah, are you doing it there? And just to show you, does anyone want to take a guess on this one? Check out how this next one executes. First perfect. I wish I could type faster. After 496, now watch this, at least on my computer in my office. dun, dun, da, 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 dun, dun, da, 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 da. And see the little icon on the lower right? Boom. And has anyone tried, just look at that. There's no perfect number. Now, do you realize how much process and what it had to do to do this? It had to go through almost 8,000 numbers, and for every one of those numbers, it had to check the divisors of all the ones up to that and add them up and see if it was that, and if it wasn't, it went to the next one. Isn't that something? Yeah, question.
There isn't a odd perfect number before 10 to the 1,500.
Is that a Wikipedia article, or is that something
I saw
you?
that, and right now I'm having my computer check all the odd numbers after that.
Oh, and by the way, before we go on, yeah, let me know about that when your computer quits or melts, one or the other. By the way, let's inspect sum from plus. Can you tell me if it's tail recursive? Can you tell me whether sum from plus is tail recursive? Yes or no?
Yes.
The answer is yes, because we don't do anything to sum from plus after we call it. And what about first perfect after? Is it tail recursive?
Yeah.
It's also tail recursive. So all that computing to get to that 8128, it wasn't making those calls. It was doing it in a loop behind the scenes. Has anyone tried the first perfect after 8128? Is that what you said? Did you say you were doing that?
I Googled it, and it's like 10 digits long.
Oh, really? Okay, now, here's another thing. Let's go back to our slides. Now, look, you guys. Notice that one thing that these are the hallmarks of pure functional programming. These are some observations that we've made along the way that we're going to summarize now. First of all, a function returns a value. Second of all, there is no call by reference. Instead, all parameters are called by value. Third, there are no loops, except behind the scenes when we do tail recursive functions, but there's no loops in the language. Instead, repetition is achieved by recursion. And furthermore, there is no assignment statement. You know, we never did say, we've been able to do all of this stuff without saying I gets I plus 1. But now watch this. Look here. If we come back to this, first perfect after, what do you notice? Do you notice something that is kind of inefficient here? What do you?
Making the odd numbers.
Well, that's inefficient too. But what about just the code itself, without any math insight? Do you see anything that's kind of inefficient?
Adding 1 to the
Yeah, we got to do n plus 1. We got to compute n plus 1 here. We got to compute n plus 1 here. We got to compute n plus 1 here. What would make it more efficient? City?
You could assign n plus 1
Yeah, if we could set n plus 1 to a value, and then just use that value instead of always computing n plus 1 each time we need it. Are you with me? Now watch this. In scheme, there is a let statement. Now watch this. I'm going to do parentheses. Let. Now, check this out. A parentheses, and now what comes, this is kind of like the condition, the COND statement. So now we're going to have a list of definitions. All right, so we're going to say, I'm going to do it simple example. X5, and then Y6, close paren, and then Z1, 1 paren. Now watch this. When I close this paren, do you see that this is a list of definitions? But I haven't closed the parentheses of the let. Are you with me? So now I can go ahead and return something. But when I return something, the expression that I return, I can use x, y, and z in there, and they will have those values. So I can return plus x, y, z, and then close the paren for what gets returned, and then close the paren of the let. And obviously, what's going to happen? What's it going to do? It's going to let x have the value. It's going to define x to have the value 5, y to have the value 6, z to have the value 1, and then do what? Add them up, and so what is the sum?
12.
So that's 12. So here's my question. Let's go up here. How can we modify this to do that? What would we do? You know, how would we modify this? Right after the lambda n, we would do what? Yes, let, paren, let, and now what do we have to do? Paren, but now it's not just paren, it's paren. Are you with me? And now what do we, let's call it, we have to give it a name. Let's call it next. So we would define next to be what? Yeah, plus n1, paren, and paren. Is that right? Okay. And then, in place of this n plus 1 paren, we can just make this what? Next. And in place of this being paren n plus 1, what can we make this? Next. And then in place of, now we've got to be careful here. In place of this n plus 1, what can we make this? Next. Now, I'm not sure I remember the command, but does anybody remember how to No, I want to reformat my, it's a weird one. How do I indent, how do I change the indentation? Does anybody know?
You can just highlight whatever lines and click tab or shift tab.
Oh, is that what it is?
Yeah.
There's a, okay, you say, and do what? Tab?
Yeah.
Oh, I didn't know that. That's cool. It indented it correctly. It re-indented it correctly. I think there is a re-indent. Here it is. Under racket, you can re-indent all. And that'll do it. That'll do the whole shebang. Did you see that? Under racket. You should do this before you hand in any code. All right. Same thing in NetBeans, by the way. You should do that with your C++ programs. Well, I mean, it'll fix it all up for you, you know. All right. So now let's run that, and let's see, what was it? First perfect after 28? Ooh, we missed our, what did we do wrong? Do we need an extra paren?
Mm-hmm.
How did that happen?
Close out the let after
The let isn't
the whole
closed
thing
all
is
the way.
done.
Oh, the let, Oh, is that why I needed the extra paren?
Yeah.
Or
Okay.
you have,
Wait, is this,
you take out a pair, I think. And
where?
you have to let paren. You can take out one that one.
No, no. I don't think you can, because it is a list of definitions.
Okay.
Are you with me? That one is not optional.
Why?
Because remember the example we did? We said let, and then we said paren, and then we said paren. The example that we used was x5, y6. So there's x5, and then y6, it was like this, and then we had, like plus x, y. Okay, so if we do this, it's 11. But see, look, if you take off, if you do this, if you take this one out, why isn't it? Oh, I see, yeah. Well, because if you take this one, here. If you take this one out, like this, and you make this 6, you still need, will this still work? See, you still need this double. Was that what your question?
Yeah.
Yeah. So you still need that. Oh, did we ever check our first perfect after? First perfect after. And what did we want to check it with? We could check it with that big one again. 28. I wonder if I wonder if it's any more efficient. Oh, that wasn't the hard one. First perfect after 496. Well, let's move on. Okay. So here's my question, you guys. We said, here, if we come back to here, we said a hallmark of pure functional programming is there is no assignment statement. Somebody always asks me this at this point in the course, in the lecture. Yeah, isn't let an assignment statement? And the answer is no, it's not. So what's different about this let compared to a regular assignment statement? Huh? Yes, it only works within the let statement itself, and there's no way to go back to it and change it. Do you see what I mean? So that's fundamentally different from the assignment statement. There's no way to go back. I mean, the assignment statement, you can change the state, but there is no way to go back and change the state. You see what I mean? It can't, I mean, it will change recursively in a new environment, but that's not an assignment statement.
If you had let x be 7, and then inside that you had let x be 5, could you do that?
Oh, those are two different x's. Are you with me? The outer, that was a good question. Are you with me? Those are two different, the x on the out, that's scoping. Yeah. So the answer is no, you can't even do it that, you can't even do that. That doesn't even work. So there really is no assignment statement in pure functional programming, even though this let superficially looks like it. Just wanted to make sure that we realize this. Okay, now, the next thing that we're going to look at is the golden ratio. So check this out, you guys. This is a fun one. Here's my question. How do you like that rectangle?
It's the best rectangle I've ever seen.
The best rectangle you've ever seen. Well, that's good. Because the Greeks, here, how do you like that rectangle? That's horrible. How do you like this rectangle? That's horrible, right? For some reason, this is pleasing to the eye. Now, do you know why the Greeks thought that this rectangle was so pleasing? Do you know how they constructed the most pleasing rectangle? The ratio of the width and the height. Do you know how they did it? Do you know how this story about how this golden ratio, how they defined it? If you do what with it? Oh, no, not in half. Oh, yeah, if you fold it somehow, but not in half. If you fold it in what way? Here, look here.
So that the left side is a perfect square.
So that the left side is a perfect square. So in other words, if the left side is a perfect square, then it's A. If the height is A, then the width of the square is A. Now what do we have? On the right side, we have another rectangle. And then what's the criterion? What do you mean the same? Yes, yeah. It also has the goal. It should be proportioned the same as the whole one. That's the criterion. Okay, so here. So then if this is B, now tell me what's the criterion for the golden rectangle? What do we know about what is to what as what is to what? Yeah, so let's take a look at the small one. You're right. So A is to B on the small one as what? As A is to A plus B. Is everybody with me on that? A is to B as A plus B is to A. Are we good? Okay, so let's do some math. What's another way of writing A plus B over A? Instead of taking out the common denominator, what do we have? 1 plus B over A. And now, let's divide the top and the bottom by what? Of the fraction part by B. So what would we have? 1 plus 1 over AB? Okay, good. 1 plus 1 over A over B. And now, what is the golden ratio itself? What is the golden ratio itself? Why did we write it this way? We have an A over B here, we have an A over B here. So what is A over B? That is the golden ratio. Are you with me? That's the definition of the golden ratio. So here what we're saying is the definition of the golden ratio, phi, is A over B. Now, does this symbol look familiar? Where did you see this before? Don't you remember there was a phi and a phi hat? Where did we run across that before? Yeah, in discrete. And what was the phi and the phi hat? Do you remember those?
One was 1 plus, and then there was 1 minus.
1 plus something. What was the 1 plus the square root of 5? Yeah, it was. Oh, good memory. Good memory. Square root of 5. Yeah. And where did that crop up? Well, we didn't call it the golden ratio. It cropped up in another mathematical. Yeah, we used this as an example of doing a proof by mathematical induction. And do you remember what the sequence was?
Numbers.
It is the Fibonacci sequence. This crops up in the Fibonacci sequence. Remember, we had a phi and a phi hat. And we did proof by mathematical induction for some of those properties. So anyway, in terms of, we digressed. In terms of phi, what do we have? So A over B equals 1 plus 1 divided by A over B. So in terms of phi, what do we have? Phi equals
1 plus 1 over phi.
Yes, phi equals 1 plus 1 over phi. Right? Does everybody see where that is? And by the way, is phi greater than 1 or less than 1? It's greater than 1. You can see.
Oh, yeah.
Right? Because it's 1 plus 1. Yeah? There's a phi hat that's less than. And what you could do is you could solve this. You could, you could multiply both sides by phi and use the quadratic equation and get the square root of 5. That would all come out of that. But instead of doing that, showing that route, what we're going to do is we're going to do successive approximations of the golden ratio. Because look, what we're saying is that phi is 1 plus 1 over phi. So here's what we're going to do. We're going to define phi sub 0 to be 1. Okay? And now how are we going to get phi sub 1? Let's go back. How are we going to get phi sub 1? Well, here's... To a first approximation, phi is 1. But what does this say phi equals? 1 plus 1 over phi. So how will we get phi sub 1? Well, not phi sub 0. it will be what? 1 plus 1 over, it's going to be recursive. It's going to be, yeah, it's 1 plus 1 over phi sub 0. Does everybody see what we're doing? So phi sub 1 is going to be 1 over 1 plus phi sub 0. So now if phi sub 0 is 1, then 1 plus 1 over 1 is 2, right? So that's a little bit better approximation to phi. But now how will we get the next better approximation? Phi sub what? 2 will equal what? 1 plus 1 over phi sub 1, which will be what? So that'll be, yeah, 3/2. Is everybody good? And then what? And then phi sub 3 will be what? 1 plus 1 over phi sub 2. So that'd be 1 plus 1 over 3/2. So what's 1 over 3/2? 2/3, and 1 plus 2/3 is what? 5/3. And then let's do one more. Phi sub 4 is what? 8/5. Okay, successively approximating. So what we want is, we want phi 0 to return 1, phi 1 to return 2, phi 2 returns 3/2, and so on, right? So let's write phi. This is a real quick one before we go on to the next chapter. So can we write phi? So let's do phi. So define phi, and what always comes here? Lambda n. And so now, what's our base case? This is a short one. What's our base case?
If equals n0.
If equals n0. And what did we return in that case? 1. Otherwise, what do we return? Plus 1. Now what? No, we have to divide, right? It was 1 plus 1 over phi, right? So it's plus 1 divides, and now divides what? 1 by what? Phi of what?
Plus n1.
It's minus, is it not?
Yeah.
I think it is. Okay, of phi of minus n1, minus n1. Print. Oops, too many. Okay, and now check this out, you guys. Let's do phi. First of all, we'll do our base case. Phi 0, that's good. Phi 1, that's good. Now check this out. If we do phi 2, we get all this fraction stuff. So instead of doing that, let's do this. Let's do divides phi 2. Now watch this. Here's a little trick. By 1.0. So now do you see that if we divide an integer by a real, that's going to convert it to a real? So is everybody clear on that? So now instead of this being 1.5, it will be 1.5. And the reason we do that is this. Check out how it converges. If we do divides, now let's just take a big one like 20. Phi 20 by 1.0. Watch what it comes out. It's 1.6180339850117, blah, 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 right? And if we do the next one, divides phi 21 by 1.0. Now watch this. It's 1.618033990175597. So do you see how close? Do you see how it's converging? It's getting closer and closer, and the more higher order of value that we get to phi, the closer it's getting to converge. And so you could actually, have it compare the difference between one and the one that went before, you know. It's because, see, look, if you don't do that, if you don't do that decimal thing, watch what this is. If we do phi 20, check this out, sports fans. Are you ready for this? 1 and 6765 divided by 1,946. Yeah, and you know, you can get really high if you do phi like 50. You know.
But then just higher numbers help you get closer to the actual value?
Yeah, and but you can see that it's converging. If you do the decimal version, you can see that as you get higher and higher, the difference becomes, you know, less and less as you go out. You see, and you can measure the convergence that way. Okay. Well, we have a problem, and it is that, when's your next homework assignment due?
Tuesday.
Oh, but what about, do we have a homework assignment due tonight? We do we?
For data structures is tonight.
Oh, the data structures is tonight. What's the assignment for?
Monday, yeah.
Oh, the next one's due Monday. Oh, yeah, that's the problem. The problem is, it's not a big problem then. The problem is that on Monday, you have an assignment to do some graphics to write a fractal. You guys know what fractals are? Mm-hmm. It's really cool. Well, but I think that it will be, it's a very short, we're only going to do a very small part of the chapter. We're going to ignore most of the chapter, but we're going to do enough to get you to write. But I think on Monday, we will have plenty of time, I mean, to go over the material on Monday that's due on Monday, if you don't mind. You see what I mean?
So you're not prepared to do our homework on Monday right now?
Well, just one problem. There are a number of problems that you have to do, but there's one problem in the assignment that requires the graphics. And you can read ahead on that and see how to do it, and I think you'll be able to do it. But for that one problem in the assignment, I think we'll have to wait till Monday before we go over it. All right, are we all done? Are we ready for a great weekend? Yeah. All filled with paradigms in our heads. Okay, good deal. See you next time.